For more physics-related videos, please subscribe. Welcome to Stellar Physics 6e. In this video, I'm going to cover black holes. This will be the final video in this series on stellar physics. Now, to really understand black holes, you need a good background in general relativity. But don't worry, for this video, you're not going to need to know any general relativity or advanced physics or mathematics. I'm just going to give a general qualitative overview of what a black hole is. Nevertheless, some of the concepts surrounding black holes are difficult to grasp and highly non-intuitive. So I've rated the physics level in this video as advanced. However, you do not need to know any advanced physics to get through this video. Let's start off by briefly overviewing the stellar life cycle so we can see where black holes come from. A star is formed when a dust cloud collapses under its own gravity, heating up until it gets hot enough to fuse hydrogen in its core. At this point, the energy released from the hydrogen fusion will support the star against further gravitational collapse. This is called a main sequence star. This is the majority of the stellar life cycle. Once the core runs out of hydrogen, the star will move on to the next stage in nuclear burning, which is helium fusion. This type of star is called a red giant. When the red giant runs out of helium, it will go on to carbon fusion. And this process of fusing heavier and heavier nuclei will continue until eventually you get a star with an iron-nickel core. At this point, further fusion no longer releases energy, and the star loses its pressure support system against gravity, and it collapses and explodes in a core collapse supernova. This will leave behind a remnant of either a neutron star or a black hole. Broadly speaking, if the original star has a mass greater than about 20 to 25 solar masses, typically this will leave behind a black hole. Now, there is another way of making black holes that does not involve stars, and I'm going to talk about that at the end of this video. For now, let's just stick to stellar black holes. Now that we know where black holes come from, what exactly is a black hole? Let's start off by imagining a spherical mass with a gravitational field. For example, a star. Let's say you're standing on the surface of this star and you want to leave the star forever, meaning you want to escape its gravitational field. In order to do so, you need to leave with an initial velocity greater or equal to what's called the escape velocity. This is the minimum velocity you have to have in order to never fall back down onto the star. And it's equal to this expression, square root of 2gm over r, where m is the mass of the star, r is its radius, and g is Newton's gravitational constant. This expression can be easily derived from Newton's universal law of gravitation. Now, Newton's law of gravity only holds for weak gravitational fields. The more general law of gravity is called general relativity. And it turns out that in general relativity, this expression for the escape velocity also holds. So now, what happens to the escape velocity if the star starts to collapse under its own gravity? Now we have a much more compact star. It's got the same mass, but its radius is much smaller, increasing the escape velocity. At some point, if the star is sufficiently compact, the escape velocity will equal the speed of light. And since nothing can go faster than the speed of light, this would seem to suggest that nothing can escape the star, not even light. The first person to notice this was a man named Pierre-Simon de Laplace, otherwise pronounced in English as Laplace. Now, Laplace didn't know about general relativity, he only knew about Newtonian gravity. And in Newtonian gravity, light is not affected by gravitational fields, nor do we have this rule that nothing can exceed the speed of light. Nevertheless, Laplace had the intuition to realize that if the escape velocity equals the speed of light, something funny must be going on here. Well, he was right about that, because in general relativity, light is affected by gravitational fields, and in fact, it does turn out that if the escape velocity equals the speed of light, then in fact, nothing can ever escape the star, not even light. So that means that no light can ever be emitted from the star for us to see it. So, this star will appear black. Furthermore, at this point, there are no forces in the universe that we know of that can counteract gravitational collapse, suggesting that this star will continue to collapse forever until it becomes an infinitely dense point, which we call a singularity. We'll talk about what exactly this singularity is in a little bit. For now, it would seem that we have this infinitely dense point with mass m, which was the original mass of the star, surrounded by this region of space from which nothing can ever escape from inside it. Now, I'm calling this a region of space because that's in fact what it is. A black hole is not an object, it's a region of space from which anything inside that region of space can never get out. That means that anyone standing outside of the black hole can never know what's going on inside the black hole, as no light or information or anything can ever get out to affect something outside of the black hole. If you're finding this video interesting so far, please like and subscribe, and consider sharing it with a few friends. The radius of this spherical region of space is equal to 2gm over c squared. This can be found by simply rearranging this expression for the escape velocity and solving for r. This radius is called the Schwarzschild radius, or the Schwarzschild radius, named after Karl Schwarzschild, who was credited as the first person to have predicted the existence of black holes by solving Einstein's equations of general relativity. So if we have a region of space from which nothing can escape, and hence nothing inside that region of space can ever affect something outside of the black hole, then effectively this region of space is a hole in the observable universe of anyone sitting outside of it. Because as far as the outside observer is concerned, anything taking place within the black hole can never be observed and will never have an effect on anything in the universe outside the black hole. So it may as well not even be there. Now already this is starting to get a bit strange. So I want to take a moment to explain exactly what I mean by a hole in the universe. When we stand on Earth, we look out and we see this enormous universe around us. And one of the ways we can observe this universe is by observing the light being emitted by faraway objects, meaning light has traveled from those faraway objects to our eye. But the universe is not infinitely old. It turns out it's about 14 billion years old. That means light has only had 14 billion years to travel. So there exists a sphere around us from which light has had exactly just enough time to travel to our eye, meaning it has traveled exactly 14 billion years to get to us. Since light travels at the speed of light, and it's been traveling for 14 billion years, that sphere must have a radius of 14 billion light years. Now actually it turns out that sphere has a radius of more like 50 billion light years, and that's due to the fact that the universe is expanding. But let's ignore the expansion of the universe for now, as that's not the topic of this video, and only adds a complication to the idea that I'm trying to portray here. The point is, there is a maximum distance we can see because light has only had a finite amount of time to travel from an object to our eye. And if we ignore the expansion of the universe, that distance would be 14 billion light years. So any light emitted beyond that 14 billion light year sphere has not had enough time to get to us yet. So we can't see it. It's dark to us. Not only can we not see it, nothing taking place beyond this sphere has ever affected us. Because the information of that event, whatever happened beyond that sphere, has not had enough time to get to us yet. So as far as we're concerned, this 14 billion light year sphere is the edge of our universe. Anything taking place beyond it doesn't exist to us yet. This edge is sometimes called a horizon or an event horizon because no event taking place beyond it has ever affected us. Now, what does this have to do with black holes? Well, the universe is filled with a bunch of black holes, and no light from within those black holes can ever get to us. So these black holes, defined by the Schwarzschild radius, are also horizons. They're also the edge of our universe, because nothing taking place within them can ever be seen or affect us. So the universe looks like a giant spherical piece of Swiss cheese. It has this outer horizon or outer edge, and then it's got a bunch of holes in it. So black holes are literally holes in our universe. Now, while both of these edges are horizons, they're horizons for different reasons, and as a result, behave slightly differently. The overall outer horizon arises from the fact that light beyond it has not had enough time to get to us, so this horizon increases with time. Black hole horizons don't obey this law, because they're a consequence of gravity being so strong that nothing, including light, can ever escape from within this black hole. They don't increase with time. Their size is determined by the amount of matter within them. So to increase the size of the black hole, you have to add more mass to the black hole. Now, the natural question to ask here is, what takes place inside of a black hole? So far, we've got this picture of a black hole being this region of space from which nothing can escape, with this singularity at the center caused by the fact that gravity inside the black hole is so strong that everything must collapse towards the center. So if you were to fall into the black hole, you would be doomed to wind up in this singularity, whatever a singularity is. Now, singularities show up all the time in physics, and generally they just mean that that's a point where the mathematical expression of your theory doesn't work. For example, Newton's law of gravity has a singularity at a radius of 0 as well, but nobody considers that to be strange. They just understand that Newton's law doesn't hold at a distance of 0. But in this case, this singularity is a little different, because we still have this fact that anything inside the black hole is going to collapse to this infinitely dense point. So what exactly does that mean? Well, to answer that, you need to know what takes place inside of a black hole. And the answer to that question is nobody knows. And nobody will ever know, because nobody can ever go into a black hole and tell us what they saw, because no signal can ever leave the black hole. The person who falls in the black hole will know what happened, assuming they will survive such a journey, but they can never tell anyone outside the black hole what's going on. Despite this, we can still speculate on what might happen inside the black hole, and what exactly is the singularity. To do that, we need to understand what general relativity is. General relativity is a theory that gravity is caused by the curvature of space-time. So both space and time, as one entity called space-time, is curved by the presence of mass, and that curvature of space-time is what we experience as gravity. Okay, what exactly does it mean for space-time to be curved? If we take a look at this grid here, this is a two-dimensional grid. In reality, the world is three-dimensional, and actually it's four-dimensional. There's 3 spatial dimensions plus time, but I don't know how to draw that. So we're just going to take a two-dimensional surface and understand that everything taking place here holds for the four-dimensional world we actually live in. So first thing we have to understand is that on this grid, every single square has the same size. So let's just say that they're all 1 meter by 1 meter wide. This is where things get a little bit subtle. How is it possible that this square has the same size as a smaller or apparently smaller square far away from this mass? When I say that a square is 1 meter wide, I mean as is measured by someone standing inside that square. So somebody standing out here will measure this square to be 1 meter wide, meaning they'll take out a meter stick and say, yes, this square is 1 meter by 1 meter. A person standing here will also take out their meter stick and measure this square to be 1 meter by 1 meter. However, neither of them will agree that the other person's square is 1 meter by 1 meter. So this guy out here, looking at this square, will say, no, that square is not 1 meter wide, it's larger than 1 meter. And the guy inside this square will say, the outside squares are smaller than 1 meter. An observer who starts off outside and falls in towards this mass, at every point will claim that the square they're in is 1 meter by 1 meter. So that's what we mean by space-time being curved. Everything gets stretched, including your meter stick. So this guy's meter stick is longer than this guy's meter stick. So your meter stick, as you fall in towards this mass, appears to get larger according to someone who's just standing here in a fixed position far away from this mass. So that's how space is curved. But in relativity, space and time are really two aspects of the same thing. And every rule that holds for space also holds for time. So the same sort of stretching is going to happen with time. A clock out here, far away from this mass, will tick at a faster rate than a clock close to this mass. So more time will go by for the far away observer than for the close-up observer. So that's an important thing to understand in relativity. Whatever rules apply to space also apply to time, and vice versa. The only possible exception is that it would appear that you can only go one direction in time, whereas you can go forward and backwards in space. So gravity is just caused by space-time curvature, and how exactly space-time is curved, we call the geometry of space-time. That just means the rules of how space-time is curved, meaning how lengths and clocks get stretched as you move around in space and time. Now going back to this singularity only arises if you assume that the space-time geometry is the same outside as it is inside, which may or may not be true. In this case, the space-time geometry outside is called Schwarzschild geometry. So if inside the black hole we also have a Schwarzschild geometry, then we get the singularity. But that may not be true. In fact, some people claim that we live inside of a black hole, which would mean that the inside of a black hole is a whole nother universe just like ours. And when we look around at the universe on large scale, we don't live in a Schwarzschild geometry. It only looks like a Schwarzschild geometry close to clumps of mass. But on a large scale, it's got a different geometry. Now, what happens if the geometry inside the black hole is also a Schwarzschild geometry, just as it is outside the black hole? In that case, we get this singularity issue. So now we have no choice but try to figure out what the singularity is. To do that, we need to discuss another phenomena that takes place in curved spacetime. Let's imagine that instead of a curved spacetime, we just have this windy road. Now I'm going to stand on this road and watch you walk along the road. I have 3 spatial coordinates. I have a front-back coordinate, a left-right coordinate, and an up-down coordinate. You, having walked along this windy road, also have your own set of front-back, left-right, and up-down coordinates. But because this road is windy, those coordinates rotate relative to mine. So in this case, your left-right coordinate is not equal to my left-right coordinate. In fact, it's equal to my front-back coordinate. And your front-back coordinate is equal to my left-right coordinate. As you curve around this road, your coordinate system has gradually rotated relative to mine. So if, for example, you tell me I see something in front of me, I have to correct for the fact that when you say in front of me, that actually means left in my coordinate system. So along a curved path, coordinate systems get rotated. And that's exactly what happens in a curved spacetime. But remember, space and time follow the same rules. So whatever you can do with space, you can do with time. So if I can rotate 2 spatial coordinates, I can also rotate with a time coordinate. And that's exactly what happens when you fall into a black hole. If this is you and you're falling into a black hole, and I'm going to stand in a fixed position outside the black hole and watch you fall in, your radial coordinate, meaning your in-out direction, and your time coordinate are going to rotate with my radial and time coordinates. And when you get to the event horizon, my radial direction will have switched with your time direction. So this portion of your trajectory towards the singularity, which as the outside observer, I initially called a radial direction, meaning a direction in space, is actually your direction in time. So when we were saying that everything that falls into the black hole is doomed to wind up at the singularity, that's not a location in space, that's a location in time. Everything that crosses this event horizon must move towards this point in time. Well, what point in time does everything have to move towards? The answer is the future. So the singularity is actually the future. So when we say everything falling into the black hole must move towards the singularity, all we're saying is it must move towards the future. Well, there's nothing particularly strange about that. That's true for everyone. That's true for people outside of the black hole as well. So we see that in this case, there's nothing particularly strange about the singularity. It only seems strange because we forgot to account for the fact that our coordinate systems rotate as you move along a curved spacetime. Great, so now we know what a black hole is, and we've taken care of this singularity business. Now I want to discuss primordial black holes. These are black holes just like any other black hole, but they're not created through stellar collapse. If they exist, they were created early on in the universe. So if we imagine that this is the universe soon after the Big Bang, soon after it was created, we still have this horizon due to the fact that light has only had a finite amount of time to travel. But at this stage, it's extremely hot and filled with radiation, which essentially means it's just filled with light. So at this point, the universe is just filled with a bunch of light traveling in all directions. Now, light has energy, and energy is equivalent to mass, and mass curves spacetime. So this light will also curve spacetime. And if you have a high enough concentration of light in some volume, such that the mass equivalent of light inside the sphere obeys the Schwarzschild radius relation, that will form a black hole. Now this black hole has exactly the same properties as a stellar black hole. It was just created through a different mechanism. Primordial black holes are theoretical. Nobody has ever found proof that they were actually made. If they were created, they would have been created early on in the universe when the universe was dominated by radiation. Now, despite not having any evidence for them, there may be some indirect evidence for primordial black holes. One candidate is dark matter. Most of the stuff in the universe is made up of this mysterious matter which we call dark matter. We don't know what it is. We call it dark matter because it doesn't emit any light, but we can still detect it via its gravitational pull. So what type of thing do we know of in the universe that doesn't emit light but has gravity? Well, black holes. So one theory to explain dark matter is that dark matter is just a bunch of black holes. And where did all these black holes come from? Well, maybe they're primordial black holes. Another possible candidate for primordial black holes is the existence of supermassive black holes at the center of galaxies. Most galaxies, particularly very large galaxies, have supermassive black holes at their center, some of them being more massive than 1 billion solar masses. And these supermassive black holes have been observed very early on in galaxy formation. So it's difficult to explain their existence using stellar black holes, because how can we make such a large black hole so early on in galaxy formation, which is also when stars first started to form? Well, one possible answer to this is that these supermassive black holes were not made by collapsing stars, but are primordial black holes. Again, this is just a theory. Nobody actually knows where supermassive black holes come from. Now, even though primordial black holes are no different from stellar black holes, there is one way we could maybe be sure that a black hole is a primordial black hole. And that's because stellar black holes have a lower mass limit. They cannot be smaller than the Chandrasekhar mass. This is the minimum mass of a white dwarf. I covered the Chandrasekhar limit in Stellar Physics 4D. So, if we ever find a black hole smaller than the Chandrasekhar mass, we know for sure that this must have been a primordial black hole. So far, nobody has ever found such a black hole. This does not mean that black holes larger than Chandrasekhar mass are stellar black holes. They could be stellar black holes or primordial black holes. So the fact that we've never observed such a small black hole does not mean there's no primordial black holes around. For one, such small black holes are quite difficult to detect. And also, it could very well be that most primordial black holes happen to be larger than the Chandrasekhar mass, in which case we cannot distinguish them from stellar black holes. So that's as much as I want to say about black holes. There's a lot more that could be said, but it would require more advanced level of physics. For example, I could get into what happens if a black hole is rotating, or if it's charged, or both. I could also talk about quantum mechanical effect, which says that actually it is possible, due to quantum mechanics, for energy to leave the black hole. And in fact, it's possible for a black hole to lose all of its mass and energy and evaporate via what's called Hawking radiation. Hawking radiation, by the way, is also theoretical and has never been observed, although people are looking for it. So this concludes this series on stellar physics. Throughout this series, we covered star formation in Chapter 1, the physics and mechanics of stars. This is really the meat of stellar physics. This was covered in Chapters 3 and 4. We covered nucleosynthesis and all the nuclear fusion stages in Chapter 5. And we ended with the final stages of stars when we covered star deaths and compact objects. That was covered in Chapter 6. Throughout the series, we had to take some asides to cover some basics of thermodynamics as is relevant to stellar physics. So if you haven't seen this series and would like to know how stars work, I would encourage you to go back and watch this series from the beginning. If you enjoyed this video and this series on stellar physics, please be sure to like and subscribe and hit the bell to be notified for the release of future physics videos. Thanks for watching, and I'll see you in the next one.